Probably cancer. Like, that's probably really good enough.
There's some people who have cancer. Onco is like the stem of the cancer.
Good day,
Some
everyone.
people just don't look at it. I'm not sure why.
How you guys doing?
Do you know what the root onco refers to?
The what?
The root onco, like the word root onco. Do you know what that refers to?
Off the top of my head.
You're not a bio person. I was trying to prove one.
How's that spelled?
Cancer?
Yes. Thank you.
I was, when you said it, I was thinking like it starts with an A.
Oh, like an oncologist?
Yes.
Oh.
See, you guys get it.
So what's the point that you're proving?
The point is that there are people in our upper level biology class that don't associate onco with cancer.
Yes.
So
What
And like
word?
they should.
I don't think I've ever heard another word that it showed up in.
Oncogenes.
Protein.
Oncogenic, oncogenes. Those are like common words though in the field of biology. So like they should know. And it's annoying that they don't.
Or they just like don't care to look it up, so they think they don't know it.
Right.
That gets me. I don't understand how people like will read something they don't know and don't have any like
It's
just
the
the
lack of
thought
effort.
to look it up. Like, oh, I don't know what this is. Like, I kind of want to know. People just like, okay, I don't know, whatever.
And
Yeah.
honestly,
Yes, I do that. I think most humans do, or at least should, because one of our shticks is pattern recognition, and if something doesn't match a pattern, that scares us.
That's what I'm saying. And like, I understand I probably do it a little more than I should, or like a normal person. Like, if I come across a word in like a general thing, I'm gonna be like, what is this? Let me look it up, or try and figure it out. No, people just go over them. I'm like,
yeah. And then they would get upset when it impairs their ability to understand something. And I'm like, well, you're not trying to understand it. Your effort is like way down here. It's not existent.
I figure if I have to carry a listening device, I might as well use it as an encyclopedia.
or when people ask what something is from like homework, and it was online homework, and they just like didn't look at the question, like readings. Like you're reading an article. You don't
Control
know
F.
something.
Control F. Google it.
It's miraculous and free.
Yes.
So that's how we're feeling today. How are you?
Your feelings are valid, and humans are dumb sometimes. Any valid needs, that said, not something that I can entirely speak to, at least usually ruder, and at least the recognizing of that particular term. Anything else you guys need or have questions about before we get started today?
It's really nice outside. Is it outside
It
today?
is. Yes, I walked to work today. I was later getting out of bed than I liked, but I forced myself to walk because it was a good day. And
Gonna
usually
get-
when I'm ready to walk, it's raining, so I just need to make the sacrifice.
Steve's
Take the nice stroll. It is a nice day.
so
The
nice.
temperature inconsistencies are driving me crazy because they are making my sinuses act up, in addition to the yellow sneeze dust up here.
I ran by a puddle and it was coated with pollen, and I was like, oh no.
My car was just covered on Saturday, and I was like, oh, this is about to be a bad week.
Although, but it's like 30, I like leave in the morning before the sun comes up. So it's like 37 degrees. But then it's like 60 by the time I get off work and leave the building. And so I'm like, how do I dress myself? I don't know.
Yeah.
Just for winter in the morning and summer in the afternoon.
Yes, the other day I walked out of my apartment in shorts, a sweatshirt, and a vest. Does that make sense?
Layers.
No.
Welcome to the South. The only consistent thing here is inconsistency.
That-
We go through 3 seasons in one day.
Yes.
It's called a talent. Look it up. Fields can bend. I was reading the last thing I read.
Yes, fields can bend, and we're going to talk about fields today. First, though, we left off with this example,
Yes.
which has been further elaborated upon. That's staying in my notes forever now.
Just in case you
we're going to start with a quick problem. Well, maybe not super quick. We're going to begin by looking at Coulomb's law a little bit, in addition to tying in some things that you hopefully can still remember from 1500.
It's a big ass.
Don't count on that.
No, it's okay. I teach 1500, so I can just reteach you. So, this situation is probably similar to something you might have encountered on a playground, wherein you use like the plastic equipment becomes electrically charged and your air ends up drifting up towards it. Similar with the metal balls that like have a belt running up them, and then you touch it and there's an electric charge. You guys familiar with that? Might have a picture of this actually. I'm sorry. Darn. No, I do. Hooray. This thing. So what is physically happening here is this machine called a Van de Graaff generator generates a charge. So the sphere itself is negatively charged. And the person touching the sphere is also going to become negatively charged. So each individual hair is now negative, and namely at the tips of the hairs, those tips now don't want to be anywhere near each other, and they will gradually space out until all the forces on them are balanced, and they just hang out in place until something else happens to them. In this problem, we're going to assume a very similar thing. These two objects have both been charged. We don't know what that charge is, but I'm going to go ahead and say that both spheres will have the same charge. Whatever Q1 is, Q2 will be the same number for the sake of simplicity. So things beginning to write down things we know and things that we want to know. Q1 is equal to Q2, and we want to know both of them. In this physical situation, the two objects are charged, and they are both hanging from strings. Gravity's pulling down, the rope is pulling up, and the electric force between the two spheres is causing them to drift slowly apart. So if there was no electric charge here, the two objects should just hang straight down. But because of this repelling force, they have moved away from each other, and they've settled into a nice comfortable spot here. These are in place. They are not moving anymore. They are just hanging out, balanced. And our goal is to, by examining the situation, try to figure out what their charge is. We know the length of the string, the mass of each sphere, how far apart the two strings are mounted to the ceiling, and we know the angle that the string makes to the vertical in this new position.
Are the angles on each side equal?
Yes, they are. Both spheres have the same mass, the same amount of charge, and they're hanging from the same length of string. So, for simplicity's sake, they're both 5 centimeters long and have a 10-degree angle to the vertical. So there's a lot of things physically going on here. The system is in equilibrium, but there's a lot of individual pieces involved. And we are going to work it together, largely as a review of these older principles that are tying in. So, there's an electric force present because both of these two objects are charged, and they are some distance apart. So Coulomb's law seems like a pretty good place to start. Force equals K Q over R squared. We're trying to find Q, and I'm going to show you a trick. Since the two Q's are the same, the difference between Q1 and Q2 is kind of irrelevant here, which means this can just be Q times Q, which can simplify to what? Q squared. They're the same number, so we don't have to find them separately. It's just, we can just rewrite that as Q squared. Which will make our algebra a little bit simpler because we can just solve for Q at one time. You can use this about any single time the two charges in a system have the same magnitude. In order to find Q, though, we already know K, because that's a freebie. We'll need to know R, and we will need some other way of approximating force electric.
Have something to do with gravity.
Gravity is involved, yes. So, analyzing this physical situation, go ahead and add these at right angles. Which of these two pieces of information do you think we should extract next, and what would be a good place to start for each?
The radius.
All right, we do need to know radius. We need to know how far apart the two spheres are. Looking at that, if they weren't charged, how far apart would they be? Very good. They are charged, though.
Use trig.
Yes, we are going to need to use a little bit of trig to find how much farther from 3 centimeters each sphere has moved. So with what we know, can we find this leg of the triangle? Okay. So 10 degrees, sine of 10, opposite, hypotenuse. Make sure your calculator's in degrees mode. That's really the only tricky part. So if you were just looking at this leftmost one, how far has it horizontally drifted from its original position? Very good. I'm going to round it off to this point. We plugged in 5 centimeters, so this number is in centimeters. And all that's left to do is just figure out the distance from here to here. So we got 0.868 centimeters, then 3 centimeters, then another 0.863. I already have one today on Thursday. Ultimately, we need to add that number to 3 centimeters twice, and that will tell us how far apart they actually are from each other. So what will that give us for our distance between the two spheres? Very good. That is in units of centimeters. We will want that in meters. So that will become 0.00476 meters.
I think it's just 1 0, because it's divided by 100.
Oh, you're right. You're right. I'm so used to things going in factors of 1,000. My apologies. Thank you for catching that. So that is the radius. We know that number. We don't have to worry about it anymore. Now we just need to figure out how to approximate force electric.
What was the gravity thing that looked like that?
So these are hanging vertically. We know their mass, so gravity has to be involved here. So it's probably time to break out our old friend force body diagram.
I didn't miss him.
Gravity points straight down. The rope is going to have a force of tension in it at this angle. And the electric force, since the two spheres are perfectly horizontal from one another, the electric force is going to point directly horizontally. So those are the three forces present on this object, and because the object is stationary, we know that they all have to add up to 0. So the way that I like to analyze these situations is we want to look at the vertical and horizontal axes, balance them, try to see what the components that are in are. So in the horizontal axis, you've got the electric force pointing to the left, and what's pulling to the right? Sorry?
No, I was gonna say the electrical force is just right there.
Like the horizontal vertical.
On this sphere, electric points right, and the horizontal component of tension will pull left. That would be inverted on the other sphere, but the numbers would be the same.
So the tension would be minus the tension?
Yes, it is worth, you do need to make sure to keep that straight, since tension isn't going to inherently be a negative number. We want to make sure to keep the sign of the directions accurate.
So then for the other one, it would be the force electric would be negative.
Yes.
Okay.
That said, finding our numbers, it won't especially matter which one's which as long as we are consistent. So the x component of the tension, go ahead and write that as t sine of 10 degrees. And these need to add up to 0. Just check real quick. Sine opposite hypotenuse. Yes, so hypotenuse times sine of 10 would tell us this length. Now we don't know what the tension is, so we actually can't find force electric from just this line alone, which is why we also need to look at the vertical axis. So vertically, similar ball game, gravity is going to pull down. You go ahead and write that as mg. The negative inside of the g will kind of take care of the fact that it's pointing down, so we'll leave it like that for now. Plus the vertical component of tension, I'm going to write as t times the cosine of 10 degrees equals 0. So between these two equations, we have two unknowns, tension and force electric. With just this information, we can now solve for tension and then force electric.
walk me through what you just wrote on the board, please?
I can. Since tension is not something we actually need as part of our final answer, I kind of skipped finding it. I solved this for t. I'm not finding a number for t, I just found what it's equal to. And then I plugged that in here.
How did you solve for t? So 9.81 is the acceleration of gravity, correct?
Correct.
Did you not multiply it by the mass of the,
That's what this m is. I haven't plugged it in yet.
oh,
So move mg to the other side, divide it by 10, cosine 10. We get 10 equals mg divided by cosine 10. That's what the tension should be equal to. I'm skipping actually finding that number because I can substitute this in for t up here. Fe minus t sine 10 is equal to 0, therefore Fe should be equal to t sine 10. Plug this in for t and we get force electric equals 9.81 times mass times sine of 10 over cosine of 10. And if I'm not mistaken, sine divided by cosine is tangent. So the way that I like to do the algebra, that cancels and just becomes tangent, and I only have to find this one number.
how do you not have a negative number on when you're solving for t? Because you would have to subtract one of those things to the other side.
You're right. I was leaving the negative inside of the 9.8. So
So the
here.
negatives just cancel out.
Yeah, let me write that out actually. Negative 9.81 times out, which when you bring it over would become positive. I apologize. That would work too. It is.
Does it, 15 has to be in kilograms, correct?
It does. In order to find normal newtons, yes, it has to be in kilograms. So what does that give us for the force?
.0259.
Very good. That is in normal newtons because this is a force. And now that we have both of those numbers, we're clear to plug them in to our original formula. Anyone disagree with this number?
I just did my math. Okay, I gotta figure out.
sheet and all that. That's supposed to be a 0. I don't know why I write those like a 6. And what's worth noting about this answer is, as you're going to the algebra, you'll eventually arrive at q squared equals blank. Then you take the square root, you'll get q equals some number. Technically speaking, when you take the square root, if you're being mathematically thorough, you would have plus or minus the answer, because the positive or the negative number can be squared to create the one positive answer. Normally, that isn't always such a big deal, but in this specific situation, it's important to note that the number could be positive or it could be negative. Because whatever the numerical answer is, even though the q's have the same number, they can also, to create the situation, both be positive or both be negative. So we can't actually tell from this alone whether or not they are positive or negatively charged. Just know the sign. We just know how big the charge is.
So it's not gonna ask us from like a question like this, or be particular about the sign of the charge? Or
Yes, if this was a test question, I wouldn't be asking you, are they positive or negative? Because with these numbers, you can't tell. I would be checking for getting to that point, and there would probably be a point worth of points on the answer, whether or not you left with plus minus. Since you don't know one way or the other, it's worth indicating that it could be positive or negative.
Is this gonna be really little?
Yes. Because again, in nature, you will never find very big charges. It doesn't take a whole lot of charge to make something like this happen. It doesn't take a whole lot of charge to make your hair stand on end. You can get pretty big electrical forces from very small amounts of charge.
Do you want a number?
Yes.
Sorry. Plus or minus 3.697 times 10 to the negative 7. You can tell me it's wrong. I've done my math wrong every single time.
That's not what I
This
have.
problem.
8.04 times 10 to the negative 8?
That is what I have,
That's
yes.
what I got.
I'm not sure what I'm talking
You know,
about.
doing
No.
really well today.
If you get it wrong, then this is where you're supposed to be.
Seriously, oh, you know what? I didn't square the bottom, that's what I did.
That might be it.
Every step of this problem, I've done something incorrect.
And that's why we're doing it in here, so that you don't make the same mistake later. As you're writing and copying and fixing, I'm going to go refill my water because I'm thirsty and this has been empty all day.
Hey guys, I got the answer. Third time's the charm.
I feel better already. Hydration's important. Seems like a natural point for a little break then, so I'll get ready for the next little chunk with you guys. Let me do for a second. As I scramble to answer this, does anyone have any questions for me before we continue today?
Does anybody know what the express sandwiches at Forsyth today?
Okay. So last time we briefly touched on the similarities between the electric force and gravitational force. This is due to, again, the fact that the forces are cousins and because they both act based on their respective type of field. So to compare briefly back to the idea of a gravitational field, you don't need to write any of this down. This is not something that you'll need for your homework. This is not any math that we're going to be doing as we leave the chapter. These slides are up here so that we can then compare electricity to this. So this math on screen right now is how the formula for gravitational field was derived. If one was looking for gravitational field, this would be its variable, and this is all the drawn out math that tells us gravitational field of planet Earth is equal to a constant times Earth's mass divided by how far away from Earth you are. This tells us that objects with mass have and exert gravitational fields. So two masses are present up here. Mass 1 is exerting a field out in all directions. Mass 2 is exerting a field out in all directions. Every single object with mass is exerting a field like this, and how strong that field is depends on its mass and how close you are to it. All objects, their field is strongest right next to them, and it gets weaker the further out you go. This is why, Earth is, you are very affected by Earth's pole, even though the sun is more massive, it's just farther away. So the sun's gravitational field does exist here, it's just weaker because of the distance. So, when gravitational fields overlap, when the fields of each of these two particles overlap, then that is what creates the gravitational force between those two objects. Most field forces are the result of two of the same field type overlapping, and now there's going to be a force between the two objects that made those fields to begin with. The exact same thing applies to electricity and electric fields. You're not going to need the in-between steps, but this shows that the same math and the same process can be used to determine the electric field strength of a particular object based on how far away from it you are. So it's the same math as before, just electricity instead. Now, the parts that you actually should write down and care about. Our formula for electric field. The official formula is kind of a three-parter because there's two ways that you can define E field directly. Now, when I mention electric field, that is a thing that we can measure. Because we can measure it, it has a variable, capital E. And E field, let me write this down. So capital E represents E field. And because it's something that we can calculate and measure, it does have a unit. It's measured in newtons per Coulomb. That's because the official definition of electric field is based on how much force it exerts on a charged particle. Before we were ever defining electric fields super clearly, we were able to take a test charge, drop it into the field, and then watch what happens. So if you had a box that you knew had an electric field in it, you could just put an electron in that box and watch what happened to make some conclusions about what the electric field was, how strong it was, whether or not it was positive or negative. So the first formula for E field, the first part of this is E field is equal to the force the field exerts divided by the charge that that field is acting on. So, say we had that, okay, we have this proton. This proton exists, we aren't manipulating it, it just exists in space. If we wanted to measure the electric field it is giving off, one of the methods we can use, because we have two formulas for E field, one of the formulas you can use is you take a test charge, this electron is going to be that test charge, and we just drop it down right here. We insert this test charge into the E field, we know what its charge is, it's an electron, and we look at the charge and we measure how much force the field is going to apply to it. Because fields exert force. They're literally force fields. It's not even really a pun. So you insert the test charge into the field will exert a force upon that charge. The amount of force divided by the charge of the particle tells us how strong the field is. If the field itself is stronger, it will exert more force on the same charge. Meanwhile, you could also insert a larger charge in the same field, and it would exert more force on that larger charge because there's more of a reaction. So that is the first way that we ever really measured E field strength. You would just have to put a test charge in and see what happens to it. The second formula, E field, so we're going to ignore the middle piece now. E field is equal to K times Q source over R squared. Say we're looking again at the same situation, but we're looking at it from the perspective of this proton, the thing making the field. From this proton's perspective, it has some charge. We know it's a proton, we know what that charge is. And the field's strength depends on how close you are to it. So if we know what this charge is and we just measure, this is a millimeter away, we can figure out with that formula what the E field strength is right there. We can also measure 3 millimeters away, figure out what it is right here. So the strength of the field depends on the charge that makes it and how far away from it you are. Excuse me. Any questions so far? It's okay if you don't know what your questions are.
I don't know what my question
That is okay. Whenever I'm on the phone with someone, they always, like if it's in an interview or I'm calling someone for information, they usually ask if I have any questions, and I always come up with them an hour after I hang up. I realize that E fields are kind of it's a harder concept because you literally can't see them. You just have to observe what they do and take word for it that they are there and that they are what's doing this. Which is why I like the simulators with the arrows on them that show what the E field is. The main takeaways are everything with a charge creates an E field. And the strength of that field depends on the strength of the charge and how close you are to it. That's the main thing. It's also worth noting E fields technically are a vector because they do point in a direction. So, little line under the E tells us vector. But it's a little bit of a weird vector in that the direction we mostly care about is either out or in. Kind of like the because charges can be either positive or negative, E fields can point in those two different directions. Gravitational fields can only really point in one direction because you only have positive mass. E fields, though, can point either in or out, depending on whether or not the object making it is positive or negative. Positives, we like to say that those point away from itself. Negatives, we say the field points in towards the negative. And so in our E field drawings, then, we show the E field lines bending from positive to negative when the fields overlap. The field wants to go from positive to negative. Most things in nature do, from one way to another. Potential always goes from high to low. Thermal energy always goes from high to low. Electrons always go from high concentration to low concentration. So similarly, E fields go from positive to negative, and they will bend to make sure that happens. So on this drawing and the drawings from lab this week, the bent arrows, the arrows that sort of change direction to make this happen, they bend because the fields have overlapped. Now they are bending and warping to make sure that they do point positive to negative, and that bending is what creates the force. So bent fields create field forces. Any questions or issues so far? Okay. Okay, before we move on, I believe I showed you these last time. So this shows field lines going either out from the object making them or into the object making them, depending on whether this is positive or negative. And as long as they have different signs, the lines will go and bend and force themselves to go from positive to negative. This does happen three-dimensionally because all fields, gravitational or electric, go out in all directions. This is just a flat representation. You could try to draw it three-dimensionally, which would show the field lines coming out in all sides and slowly trying to bend their way over to the negative. It's not the best drawing in the world. We also have drawings of what happens when you have the same charge. So this would be like a positive trying to go to a positive. The lines don't like that, so they're going to bend and try to avoid it. And that bending away from each other is what creates the repelling force. And the people who made these drawings just decided to start getting creative with shapes. What these shapes can tell us, though, is that when an object creates an electric field, the field tends to be perpendicular to the surface that made it. So this flat object, the lines come perpendicularly out of it. This round object, they come perpendicularly out of the surface, but because it's a slanted surface, it's going to slant with it. So fields depend entirely on the thing that made them, is the general rule. Sorry, I made my sample question mixed up. The sample I wanted isn't in here, so I'm just going to bring one. There we go. Okay. We have a proton. Proton is going to exert an electric field out in all directions. Because it's a proton, we go ahead and list its charge again. Positive 1.6 times 10 to the negative 19 coulombs. My first question is just, what is the strength of this proton's E field 1 centimeter away from it? Strength of the E field 1 centimeter away. I need a new red marker for now. What number do you have?
Take this with a grain of salt. 1.438 times 10 to the negative 5. That's
What?
really,
I
or
will
really
not
strong
take this
today.
with salt because it's correct. So that is the strength of the field created by this proton at that location. Once again, what are the units of an E field?
Newtons per Coulomb.
Newtons per Coulomb, yes. We use this unit because an E field exerts force on coulombs. And that is our first calculated E field. Next question. I don't want you to change what's in your notes. I don't want you to erase this question. But hypothetically, what would be different if we examined a spot 2 centimeters away? I don't have any space to draw that way, so I'm just going to put the 1 centimeter up in the middle here.
I think it's about like power of 10. Not exactly.
Sorry. Not a drop-off lecture unless something gets dropped.
At least you're consistent.
So what I've got is, you're right, it's at least a factor of 10 different.
It's weird calling.
Now, what I ask you to do is, while this number is still in your calculator, multiply it by 4.
Okay.
And we get the first answer.
Wow.
When you move twice as far away, the field becomes 1/4 as strong. Because like with the electric force formula, the R term is on the bottom and it's also squared. So the farther away you get, the exponentially weaker the field gets. The field is at its strongest when you're very, very close to the thing that created it. But as long as you know the charge that's creating the field and how far from it you are examining, you can determine what the strength of the field is in that location. Excuse me. So, I'm going to draw in those field arrows. Along this line, the field is just continuously pointing this way. Field is a vector, it's pointing in a direction. So, as far as these two locations are concerned, the field is pointing in the positive x direction. The thing about electric fields is, since they're vectors, fields from multiple sources can overlap and add together. So again, don't change anything in your notes. I'm just going to change the one picture up here because I only have so much board space. What do you think would happen if we put a second proton in the space 2 centimeters away? What would the field be in the original 1 centimeter point? Sorry? Almost. So, in this location,
Non-existent, 0.
you're right. I'm going to explain why though. So our original location is now 1 centimeter away from 2 different protons. It's directly in between them. The first proton by itself is going to exert this much field to pointing in the leftmost direction in this particular spot. The second proton, because it has the same charge and is the same distance away, will exert the same strength of field in the opposite direction.
So they cancel out.
They will cancel out in this spot specifically. They are vectors, they add together.
But the charge would be more positive, correct? At that spot?
Not exactly. A location, like a location of empty space doesn't have a charge. An object has to have a charge.
Drew, what was the thing on the simulator measurements? In between,
Voltage.
what is that?
Voltage is kind of like water pressure for electricity. The higher your voltage is, the more the system is going to push electricity through it. Excuse me. And electricity always wants to go from high potential to low potential. In the simulators, when you had, say, a proton here and an electron here, you would measure positive potential next to the proton, negative potential near the electron, and 0 in the middle. That tells us that in this situation, a proton would want to go from the positive potential to the negative potential.
So directly in the middle would be 0.
The potential would be 0, yes. But
I think that's what I read on our lab, so.
in that situation, since
Right.
there's an even lower potential near the electron, the proton would keep moving. If you had a proton and an electron and sat a proton between them, the proton would drift towards the electron.
Why would it do that? Like, I get logically why it would do that, but I don't think numerically why the 0 wouldn't mean that nothing happened.
Because next to the electron, the potential is even lower. Everything likes to go from high potential to low potential, and negative is lower than 0. In this case, though, both of these are protons, meaning we have positive potential here, and 0 potential here. A proton will just hover in the middle because both sides are higher than 0. A proton doesn't want to go near either of these protons, which is why the E field here is just ultimately canceled out and reduced to
But
0.
wouldn't the voltage be positive?
In this spot, voltage should be 0.
Because like when we did that on the thing, like if it was 2 protons, the voltage was positive. It was like 35, and if it was 2,
That would just be the lowest point then. Okay. I'm sorry, I didn't mean to tie voltage into this because we're going to talk more about that later. So I apologize for mixing the metaphors. The important thing for this example is field lines add up like vectors. So the electric field at this spot would add up to 0. And you can actually see that in these field diagrams. So these are the two that repel each other. These are like charges. Near either of the charges, the lines are pretty clearly defined. You can see the lines, you can see the field, you can see where it's pointing. If these are the same charge, if these were both protons, then this would be sending field this way, this one would send field this way, and they would cancel out in the middle. Which is why this area here, where the fields would add up to 0, doesn't have lines. It's just murky and poorly defined. I know this projector makes things fuzzy to begin with, so it might not be super easy to tell, but are you able to see that this region right here is less sharp, is less pointy than the field lines closer to the sources?
Yeah. On the open circle one, the whole middle was fuzzy like that.
Correct. Good point. The open circle, the entire center is fuzzy. Because if the surface of this ring is exerting a field in every single direction, then every part of the surface is also exerting a field inwards. But all those arrows pointing directly in are just going to add up to 0, which is why the inside is that murky, ill-defined zone. All the field created by the ring itself is overlapping and adding up to 0 in the center. So fields can combine and add up to either, well, they will just add up. It's possible for one field to overpower another, and let me show you a slightly different example. We're not going to work it all the way through, just want to at least show it to you. Okay, yeah, this is just a good concept example. In this situation, we have 3 charged particles. 2 negatively charged particles with the same strength, and 1 positively charged particle with double that strength. Each one is exerting field in all directions, and we want to look at how those fields are going to add up right here. Some of our work so we can draw on the picture. So if we're just looking at one particle at a time, from the perspective of this spot, this particle is going to pull field in this direction. Because it's negative, it'll pull towards it. This particle is also negative, so that's going to pull towards it. The positive particle, positive pushes away from itself, so it's going to push in this direction. So the question is going to be, how do those add together? And we could sit and do all the math and the algebra for it, but just your first instinct, based on the fact that this particle is going to be further away than the other 2 are, what's your first guess as to how the field's going to add up in this spot?
Negative.
Got 1 for D.
But even though it is further, since there's like still 2 going.
It's okay. This one's, well, I'd like to do the numbers with you, but I don't want to keep you today. In this situation, the answer is D. due to the fact that this line is slanted, so this is the hypotenuse. It's when you divide it up into its x and its y, those are going to be smaller than the hypotenuse itself. And it's contending with the combined forces of two things that are closer to that zone limit. All this to say, they add up like vectors, which is why we did a trig example earlier.
Big sense.
I know these concepts might still be a little weird. So while working on the homework, please send me any questions you have. I'm totally fine if we spend Tuesday continuing to do these examples, looking at the homework problems. If we need more time on this first electrical assignment, I will push the homework back by a day or two. So do please let me know how you're doing, what questions you have, so that I know how to best calibrate moving forwards. And if I don't see you again today or tomorrow, you please have a wonderful weekend as well. Maybe inconsistent weather prove at least pleasant.
It's supposed to be nice and cold when I'm working outside on Saturday. It's colder than it is right now.
We need a 7 on Saturday.
See what?
We need a 7 on Saturday.